You know, I'm beginning to understand the book now. We did a lot of review, and it feels like there's a lot of overlap where we're headed right now. I apologize if anyone feels like they're repeating myself. But that be it as may, we're gonna look at some stuff I've mentioned, but we're really gonna beat it up. We're gonna really beat it to a pulp today. The main subject is real zeros of polynomials. We're going to learn something about the zeros, about the roots, and also how to find them. We're going to start with a simple example. I have a polynomial, and I know it has zeros at 2, 3, and minus 4. And I'm going to try and construct that polynomial. Any ideas how I would construct that polynomial? Yes, John?
X minus 3 times x minus 2 times x plus 4.
Thank you. Anyone understand that? I know these are the zeros, and there's clearly a polynomial where they are the zeros. But I'd actually like to look at that in a standard form, so let's go ahead and do a little work. So I'm going to FOIL this. It's going to be x squared minus 3 and minus 2, so minus 5x plus 6. Multiplying this is a little more work, but I can do it. Get x cubed minus 5x squared plus 6x plus 4x squared minus 20x plus 24. I just distributed x over this and 4 over this. And now I can collect my like terms. So that's minus x squared minus 14x plus 24. So I want you all to observe something important about this polynomial with respect to these roots. The first part might be a little obvious. The constant term 24 just happens to be, ignoring the sign, the product of 2, 3, and 4. 2 times 3 is 6, times 4 is 24. Now, I say it should be a little obvious because if you think about how I go about this multiplication, 3 gets multiplied by 2, getting 6, there's that 6, and then that gets multiplied by 4, and that's how I end up with a constant term. It's just multiplying the constant terms. A little less obvious, but kind of obvious, is that the coefficient of x cubed here, which is 1, is the product of the coefficients of the x's, 1, 1, and 1. I mean, if you think about that in reverse, if one of these had a non-1 coefficient, it would appear here too. So, okay, that's a nice observation. Here's one you might not have thought of. Might be a coincidence, but if I add these up, 2, 3, minus 4, I get minus 1. That This happens to be the coefficient of the second term. Maybe that's a coincidence, right? We're going to look into that. So how are we going to explore this? Well, we're going to look at a very, very general polynomial. We're going to say p of x is equal to some leading term a0 x plus b0 times a1 x plus b1 all the way out to a to the n x plus b to the n. This will be an nth degree polynomial because ultimately I'm going to multiply x times x times x times x n times. Okay, that's good. What else can we tell about this? Well, clearly the leading term is going to be a0, a1, a2 times a to the n times x. There'll be some other terms in the middle. And the constant term is going to be b0, b1, b2, all the way down to p to the n. Right? So that observation about, that we saw here isn't really all that surprising. Maybe there's a little more we could squeeze out of this general polynomial. Let's look at let's just look at the first two terms multiplied together. Term is not the right word. So this will be a0, a1 x squared plus a1 b0 plus a0 b1, a1 b0 plus b0 a1 times x plus b0 b1. Okay. Again, that's following our pattern. Maybe jumping the gun here. But if these a's were 1s, then the coefficient here would just be the sum of the b's. Kind of like we saw here. And this still may be an accident, but let's give it one more shot. Let's multiply this by a2x plus b2. Well, we know what this term is going to be, a0, a1, a2, x cubed. And we know down here we'll get b0, b1, b2. These terms in the middle take a little work. And I'm going to be lazy. I'm just going to write them down. Here we have a0, a1, b2 plus a0, a2, b1 plus a1, a2, b2 times x squared. I have to sneak in the next part. a0, b1, b2 plus a1, b0, b2 plus a2, b0, b1 times x plus b0, b1, b2. Okay. So there's a few observations one might want to make about these middle terms here. First one is that, again, if all the a's are 1, like we had here, then this term here is exactly b1, b2 plus b, oh, made a mistake here, b0. It's the sum of the b's, right? Plus minus 1. But there's a little more. This particular polynomial, it's degree 3. There are 3 terms here. And you'll notice each of these has 2 a's and a b. And it has 1 of each. 0, 1, 2, 0, 1, 2, 0, 1, 2. That's the x squared coefficient. The x coefficient, on the other hand, has 1, each part of this has 1a and 2 b's. And again, 1 of each, 0, 1, 2, 0, 1, 2, 0, 1, 2. So there's some kind of pretty symmetry going on there. I'm not going to do the next one. But you can kind of see where this is going. These intermediate terms are going to be the sums of the products of the a's and the b's. Clearly, the next round, this will have 4 terms, right? There'll be another term in the middle. Anyone want to guess how many things I'm going to have to add up? Middle term. This is actually within the scope of your ability to guess. If you remember a fellow by the name of Pascal. Anyone remember Pascal? What's Pascal famous for?
Pascal's triangle.
Pascal's triangle. Who here has never seen Pascal's triangle? Okay, 30-second digression. Pascal's triangle looks like this. You start with a 1, and then you put 1s around the edges. And then in the middle, you add the 2 on either side. 1, 3, 1. These are really useful if you multiply x plus 1 to the n, right? Here you have x squared plus 2x plus 1. Here you have x cubed plus 3x squared plus 3x plus 1. Can you see where that's going? And so if you look at the next level, 6, 4. So if I multiply this by a3x plus b, the middle one will have 6. 6 things we'll have to add up. Okay, so where is this all going? This is interesting, pretty stuff, but we really don't need most of this. Not today. All we really need is right here. Before I tell you what we're going to use here, let's look at what were the roots of p of x. Can someone give me one of the roots of p of x, this general polynomial? Someone looking at a computer, tell me one of the roots. Well, if I said 3x plus 2, what's the root? This is a factor. What's the root? Anybody? -2. Is that your -3/2? Okay. So what are the roots from this? Negative B0 over A0. Okay, so that's one of the roots. You get a B1 over A1, and so forth. B to the n. Now, if I just give you a polynomial in standard form, we need to factor, right? That's what we want to find. You don't know these. But you do know the product of the b's and the product of the a's. So if you look at this particular construction, b0, b1, b2, b to the n, over a0, a1, a to the n. We don't cancel anything, we just look at this. We know something really important. We know that, what? That embedded in here are these roots, right? Oh, a0, right? Forgetting the negative signs for just a second, we have b0 over a0, but we've got that here. Okay. This brings us to the rational root theorem. The rational root theorem says if we have some polynomial, right, in this form, and we look at the leading coefficient, oh, it should be x to the n, on the largest x, and we look at the constant term, then we can limit ourselves to possible rational roots. They would have to have a factor from the constant term and a factor from the leading term. That's if there is a rational root. There may not be, right? We may not even have any real roots. But if we have a real rational root, we can narrow it down. Okay, let's see a practical example of this, because this is all very abstract. We want something we can use. So let's look at this example. P of x, polynomial, is equal to x cubed minus 3x plus 2. And I want to know if there are any rational roots. This will have a real root. Does anybody recall why this? I know this will have a real root. We talked about this a few days ago. Maybe Monday, I'm not sure. How do I know that that has to have a real root? It can't all have imaginary or complex roots. Nobody remembers, okay. Well, here's the argument. I know the end behavior of this guy, right? As x gets great, he's going to go off into lambs. As x gets negative, he's going to go very negative. And he's smooth and continuous. So somewhere, he has to cross the x-axis. So anytime the degree of your polynomial is odd, you have to have a real root. Okay. Well, that's not really what we're looking for here. We're looking So the rational root theorem tells me I want to look at this coefficient and this, which is 1. And I want to look at what are the possible factors involved here. Well, 1 over 1 is always a factor, but it could be negative 2, right? So negative 1. 2 over 1 is a factor, and negative 2 over 1. And thankfully we ran out because this list could get very long. Okay, so what we know from the rational root theorem is we can try each of these, and if we don't find any, there are no rational roots. But we might find a rational root. So how are we going to do this? We're really looking to factor this, right? So the factor theorem tells us if I just plug the number in and I get 0, I have a factor. So where should we start? Oh, remember from the last class. It's too easy. Start at 1, right? I want to do the easy calculation first. So 1 cubed is 1, minus 3 times 1, minus 2 plus 2 is 0. So already I found a rational root. That wasn't that hard. I have a rational root. The factor theorem tells me that p of x has to equal x minus 1 times some q of x. So I want to know what q of x is. So I want to divide p of x by x minus 1, which I learned to do using synthetic division. Right. So I bring this down, I add, multiply, add, multiply. Oh, good, I get a 0. If I didn't get a 0, I've done something seriously wrong. And that tells me that q of x is x squared plus x minus 2. These are just the coefficients of the quotient. All right, now I'm almost done, right? In fact, I'm on easy street because all I have to deal with is a quadratic. And I can always factor the quadratic. Even if it's not going to give me real roots or rational roots, I can always factor it using the quadratic formula. So the coefficients here are 1, 1, and minus 2. So negative b plus or minus square root of b squared, right? Minus 4ac, that's minus minus or plus 8 over 2. Minus 1, this is going to become 9, square root of 9 or 3 over 2, or what is that? It's going to be 1 or minus 2. So I know my factors are x minus 1. Well, I have another x minus 1, and I have an x plus 2. So that's how we can factor something using the rational root theorem. Very handy if you've got a polynomial with degree greater than 2, greater than a quadratic. And it doesn't always work. It may not work. But at least you have something to try. Okay, not all these problems are quite this simple. We should try something a little more difficult, just to see if there are any new problems we might come across when we're trying to do this. So let's instead of this polynomial, let's look at something a little more daunting. How about 2x cubed plus x squared and 13x plus 6. So the constant term over the leading term is 6 over 2. And factors of 6 are what? 1, 2, 3, and 6. Factors of 2 are 1 and 2. And then we always have to watch out for a negative. So what are the possibilities here? Well, we can have 1 over 1 plus or minus, 2 over 1 plus or minus, 3 over 1 plus or minus, and 6 over 1 plus or minus. But we could also have a 2 in the denominator, plus or minus 1 over 2, plus or minus 2 over 2, well that's just 1. We already have that. Plus or minus 3 over 2, and plus or minus 6 over 2, that's 3, we already have that. So now we're down to 1, 2, 3, 4, 5, 6, 12 possibilities. Now, that's a pain, right? It'd be a pain in the neck to have to go through every single one of those. But if we could, and we could find out, is there a rational root? We might find out there are none. We might get lucky. All right, let's start with 1. 2 plus 1 is 3, plus 6 is 9, minus 13. So that's so much for plus 1. Minus 1. Okay, minus 2, plus 1, minus 1, plus 13. 12 plus 6, no. Okay, so these are out. Hope I don't have to go through all of them. When I get to 6, I'll have to multiply 6. I know what 6 cubed is. Does anyone know what 6 cubed is?
2016?
Yeah. Yeah, didn't that come up on a homework problem or maybe on the exam? Okay, let's keep going. Let's try 2. So 2 cubed is 8, 2 is 16. I have to write this down. Plus 4. Minus 26 plus 6. 20 plus 6 minus 26. Oh, look at that. Plus 2. It's going to work. So plus 2 is a root. What's the factor?
X minus 2.
Yeah, x minus 2. To find the rest, I have to divide by x minus 2. Well, I'm beginning to like synthetic division. You know, they didn't teach it to me in grammar school. This. Okay. 2, 2, 4, 5, 10, minus 3, minus 6, good, 0. Right. So now I know I get 2x squared plus 5x minus 3. Well, once again, I'm in this lovely place where I can use the quadratic formula to find these roots, right? This is my a, my b, and my c. So negative b plus or minus the square root of 25 minus, but there's a minus, so it's going to be plus 12, 24. Recognize that number all over 4, 2a. And this is 49, so the square root of 49, of course, is 7. So negative 5 plus or minus 7 over 4. Negative 12 would give me negative 3, and 2 would give me 1/2. So now I know the factors are x plus 3 and 2x minus 1. So that is the rational root theorem, how to use the rational root theorem to find the factors of a polynomial. As I said, you might not have a rational root. Yeah. I don't know, this came from the air somewhere earlier. Rational roots. First, does it have a real root? Yeah, because it's odd. It has to. It was even, we don't know. Does it have any rational roots? Oh, it's pretty easy. It's 3 over 1, so it can only be plus or minus 1 or plus or minus 3 over 1. Well, clearly 1 and minus 1 don't work, right? Clearly 3 and minus 3 doesn't work. So I know right away this has no rational roots. That's helpful. All right. About being the second class of the day for me, for you guys, is that I've already done this and I already know, I don't know whether the key's going to work, but I already know how things evolve here. So I know that I have to kind of do a song and dance here for a minute while the computer comes up. My next explanation. So what I want to say while I'm doing this stuff is that if you look at the book, this chapter, which I always recommend people look at the book. You'll find some of the things I've said, and you'll find some of the things I say aren't in the book. The book goes on to describe 2 additional techniques one might want to use when using the rational root theorem. They don't add anything really new. I mean, they're kind of neat things, so I wouldn't say don't look at them, but they're hard to use. And all they do is they try and narrow down this list here for you. Right? You can get a very long list, and maybe some of them, for various reasons, are not. They're not going to pan out. So, in particular, they tell you about Descartes' rule of signs. Trying to use Descartes' rule of signs, I mean, you might do it on a homework problem, you might look it up, and you might figure it out, but you're not going to remember it. I mean, there's no reason to remember it. You just go through and check all your rational roots. It doesn't get you to a root. Well, it gets you to the root a little quicker after you've gone through this whole song and dance. It's neat, though. Anything with Descartes' name attached to it has got to be pretty good. Important mathematician. Same with the upper and lower bounds theorem. You know, it's going to give you some way to say, well, the root has to be between these two values, so anything larger or smaller is not going to work. So again, it could in theory speed you up. If you're going to go into some kind of Olympic competition solving polynomials, you might want to do that. From my point of view, it's just like more stuff to cram into your head and have it fall out a month after the class is over. So don't feel obligated. If by some accident one of the homework problems turns up with Descartes or the upper and lower bounds theorem, send me an email and don't bother, quite honestly. Okay, so those are other techniques that that the book talks about. But one thing they mentioned, which I think is really valuable, is to use a computer system, or a TI calculator. If you've exhausted rational roots and you're looking for real roots that aren't rational, and you don't have a way to do it, this is a great way to do it. The TI computer has in the calc function, I think we looked at that. It'll find a 0 for you. Let's take a look at, this is Desmos, but you can do something similar with Grapher. If you don't have the internet handy. So here's my polynomial, 3x to the 4th plus 4x cubed minus 7x squared minus 2x plus 3. Not really sure what's going on here, so let's zoom out a bit so we get a big picture of this. Okay, so you can see right away there's going to be two zeros here, right? It's going off. It's not coming back, right? In theory, it could. We could zoom out some more, but it's not. You can tell that because the coefficients aren't very big, right? You have some very big coefficients on there. Maybe somewhere out here it's going to come back down. So we have a 4th degree polynomial, and it's got 2 roots. That's good. We know that. We'd like to know what they are. So now let's zoom in. And this is a little hacky here. Use a mouse and a plus key. I'd like to just know the number. I think actually Desmos will tell you. I think, yeah, he will. He'll give you kind of a value there. But you can just keep zooming in, and up to a certain point, he'll give you a more and more accurate number. Where are we now? We're down between 2.36 and 2.38. And looks like, let's go a little closer. I'm just going to say this is a really good way if you just need a practical answer. You just need to know what a root, what the root of an equation is. This would be for a real world problem. In mathematics, often we want the exact value. This is inadequate. Although it can give you a starting point to look too. That's another nice feature of a calculator. So looks like 2.363, and then it's got to be 9 something. So technology is your friend. I guess that's the the moral here. I want to leave. Okay. All right, any questions about using the rational root theorem to find real roots of polynomial? Because we should all be almost expert by now, right? Yes.
So what we going to try to solve for this?
Not today. I mean, one of them is real easy. One of them is real easy. X to the 7th minus 3 equals 0, and x to the 7th equals 3, or x equals the 7th root of 3. But there's 6 more. We don't really have the tools to do that yet. Right. So now we're going to remove this restriction, real zeros, and we're going to talk about complex zeros, polynomial. And to start off, we have to look at something important. You know it's important because it's called the fundamental theorem of algebra. Sounds pretty important, doesn't it? The thing about the fundamental theorem of algebra is it feels a little incomplete. It feels like we need something more. But here it is. The fundamental theorem of algebra says every polynomial p of x has a root. Or reading the book, it'll say it has a root over the complex numbers. Now, it might not have a real root, but every polynomial has a root. That is, there's some c, e of c equals 0. It doesn't feel complete. We need a little more. And in fact, we're going to talk about the more right now. See, if I have a root, I'm going to call this C1, then I know something about this polynomial. I know a factor, right? I know p of x has a factor, x minus c1. So P of x is C of 1 times some other polynomial. I think it should be clear that if P of x has degree n, just kind of put an n here, then Q of x has to have degree n minus 1, because I've divided out one of the x's. Well, but the fundamental theorem of algebra applies just as well to Q of x. Right? Q of x has to have a root. Let's call that C2. So now we know that P of x is x minus C1 times x minus C2 times, I guess we'll call it R of x. Again, degree less. Right? And we can keep doing this. Right? We keep doing this until we have what? We have n roots. So we have what we call the complete factorization theorem that says that a polynomial of degree n has n roots. Again, you know, over complex numbers. Okay, well, maybe now this fundamental thing makes a little more sense. I mean, this is a corollary. I'm going to ask you if you know what a corollary is again. This is a corollary of the fundamental theorem. And it tells us something really beautiful, right? We've got a polynomial. It's degree n. I know there are n roots. Now, I think we talked about this before. They could all be the same, right? X to the 7th equals 0. It has 7 roots. Well, it has root 0 of multiplicity 7. I'm getting ahead of myself. Maybe those roots are real, maybe they're not. If they're real, maybe they're rational. But it doesn't matter, we know there have to be n roots. So that's the complete factorization theorem. Unlike the rational root theorem, it doesn't really, it gives us confidence to go looking for those roots, but it doesn't really give us a way to find those roots. That's kind of the next step. We'll look again at how to find our complex roots. But I guess that's all I have for you today. There will be a homework assignment. I'll try and post it tonight. It won't be due till next Monday.